Alright, Electrostatics Lecture 2. This one will be about electric fields. So let's look at an example of electrostatic forces. I have these two charges, they're 0.3 meters apart, and we've listed the charges of each one. Now, let's say for the second that we are using this charge, 5 Coulomb charge, which means it has a shortage of electrons. And this charge isn't going to go anywhere. This is a permanent charge. It's attached to something. Right? It is fixed to this point right there. And I bring other charges near it. So I bring this smaller charge, 0.07 coulombs, near it. And if I held it there, I would have a force of 3.5 times 10 to the newtons to the right on charge 2. They are like charges, so they're going to repel, so it means it's going to get pushed to the right. And you should be able to do this math, right? This is the last section. Now, I don't change this charge, but I decided I want to use this charge to basically shoot other charges around. So after this one gets put here at 0.3 meters away, it has this enormous amount of force placed on it. I let it go, it's going to go flying off, and it's going to accelerate to the right. And then I get another charge, still not moving this one. Now I put a smaller charge there. I put it at the same spot, I hold it in place. This one now has a charge of 0.01 coulombs, where the last one was 0.07 coulombs. Well, I can still calculate the force. And this time it's going to be a different amount of force, but this one will also be pushed to the right. And I could calculate this force with the same equation we had for electrostatic forces, right? K, Q1, Q2 divided by R squared. Now, I'm doing the math for you, so this is nice and easy. But if we wanted to figure out these forces, we'd have to use the equation and do the math over and over again. So with me doing the work for you, it's not so hard, but if you were calculating this, right, then you would have to take your two charges, you'd have to multiply it by K, Q1, and you'd have to divide by the distance squared, which all of it in itself is not that hard to do. But still, you'd have to do all this to get this, right? And then that would now tell us how hard it's getting pushed. And again, if we let it go, then it would start moving to the right and accelerating to the right. If I, again, left Q1 where it is, and I move something else there, well, now I would have, so I have a charge that's a negative charge. This has an excess of electrons. Again, we could calculate the force on it. But if we think about it, I'm not moving this at all. This is part of the equation. And I'm not changing this at all. This is part of the equation. The only thing I'm changing is one number. So if I keep going back to this equation, I'm doing a lot of work, which is not necessary every single time. If I know that this isn't changing, the distance, and I know this isn't changing, charge 1, and I know K is not changing, there's a lot of things in these calculations that I had to do to get these numbers that don't change from problem to problem to problem, right? And this is a kind of a common situation in the real world where we have these set amounts of charge somewhere, and we use that charge to project or to push other charges around. And we don't necessarily know what the other charges are going to be every single time. Now, this is a simplistic version, but this still happens. And we'll see, hopefully we'll see examples where we set up these charges that are going to now push other things around. We don't change, right? We don't change the thing, the charge that's going to do the pushing for us. But there's a lot in this equation that doesn't change. Again, I think I'm repeating myself, but again, this didn't change, K. Q1 didn't change, R didn't change. So there's a whole bunch of this equation that stays the same for all three examples. So what does that mean? Well, it really means that we could come up with a new measurement. If we knew this, K Q1 over R squared, and we just kept that and said, hey, at this point, these three things, I can calculate them, and then every time I bring a different charge over, I can just multiply that charge by these three things that aren't changing. So these three things have a name to them. This is what we call the electric field. The electric field is the electric force per charge at a specific distance. I don't know what I'm going to put here, but I could still calculate the electric field, which means I know K, I know Q1, I know this charge, and I know how far away I'm going to put things. That's the electric field. Now, this is the first equation. This is if I don't know what I'm going to put there, but I do have this set up, right? If I'm assuming I have this set up, I have my charge. I know what distance I'm going to bring other charges to. Well, I can calculate the electric field there. I can calculate the force per charge. And let's just say for a second I did some math and I get a force per charge, and it works out to be 5 newtons per coulomb. Let's just say that's what it was. Well, that means if I put a coulomb of charge there, it would experience a force of 5 newtons. If I put 2 coulombs of charge there, it would experience a force of 10 newtons. A half a coulomb of charge, 2.5 newtons, so on and so forth. Right? It tells me how much force per charge I would experience there. Now, the other way to do it is, what if I knew this force? What if I knew I put a charge there and I knew the force on the charge? Right? Let's say that I put a 1 coulomb charge there and it experienced a force of 5 newtons. Well, the other thing I could do is I could see how much force there was and what was the charge, and I would say that this is charge 2, really. But if I knew the force on this and I knew its charge, I could then get the electric field. So let's back up for a second. I have this. I have a force of 3.5 newtons, 3.5 times 10 to the 10th newtons, and I know I have a charge of 0.07. So if I took the 3.5, the force, and divided it by the charge, I can get the electric field. How much force per charge is being exerted there? So 3.5 times 10 to the 10th divided by 0.07 is going to be a huge number. This is going to be, hold on, there we go. So what would this be? This would be 5 times 10 to the 11th newtons per coulomb. A lot of things move around here. Let's see. Come on. So at this location, because I know I have a charge and I know I have the force on that charge, if I took the force divided by the charge, I could say at this location, this charge is exerting 5 times 10 to 11 newtons of force per coulomb charge that I put there. So let's take a look at this one. I have a charge of 0.01 coulombs, and I have a force of 5 times 10 to the 9th, so I take 5 times 10 to the 9th divided by 0.01 coulombs. Guess what I get? I get the exact same number. This turns out there's going to be 5 times 10 to 11 newtons per coulomb at this spot. I do the next one. I get a force of 2 times 10 to the 10th. 2 times 10 to the 10th divided by 0.04. Guess what I get? I get the exact same number. So in all these cases, if I take the force divided by the charge, I get this number. I get this number. At this location, there is a force of 5 times 10 to the 11 newtons per coulomb. So if I know the charge there that's getting pushed, I know how hard it's getting pushed and its charge, I can figure out its electric field, the force per charge at that location. But what if I did it a different way? What if I just looked at this? Because this is the one that's applying the force, and I did K Q1 divided by R squared, because these are the 3 things that I don't know. I'm sorry, these are the 3 things that I do know that won't change. So I have 9 times 10 to the 9th. And then I multiply that by 5 coulombs, and I divide that by 0.3 divided by 0.3, or divided by the distance squared. I get 5 times 10 to the 11 newtons per coulomb. My point being that if I know the charge that's going to do the push in and the distance that I'm going to put other things away from it, if I know this and this, well, then I could use this equation. If I know the charge that's being pushed and I know how hard it's being pushed, if I know information about this charge, how hard it's being pushed and what it is, then I can use this equation. Either way, it'll still tell me that at this point, what's the force per charge. So electric field, like electric force, is a vector. The problem is that some things are going to get pulled to the left, some things are going to get pushed to the right. So I'm dealing with an electric field, but there's two possible directions that charges can get pushed or pulled. But the electric field is completely independent of what I put it there, right? Regardless of what I put at this point, the electric field stayed the same. So I have to establish a direction for electric field even when it's doing nothing. So in all cases, the electric field or the direction of the electric field is always in the direction a positive charge would move, regardless of whether there's a positive charge or there or not. Right? In some ways, I imagine electric field kind of like a sci-fi movie, like a force field, right? If you see like Star Wars or Star Trek or any one of them, right? And they have their force field on. Well, if they're just flying around and their force field's on, their force field's not doing anything, right? It only reacts when something's there to react with. Electric field is kind of the same as that. The electric field is there, but it only reacts when there's something to react with, right? So if I had a positive charge and it was just sitting there and there was nothing else near it, there's still an electric field. There's still a force per charge at distances away from this, even if there's nothing to push on. So if I established here and I said, okay, at this point, what's the electric field? There would be one. There'd be a certain amount of force per charge. And what would the direction be? Well, the direction would be away, because if I put a positive charge there, it would move away. If I put a charge here, if I want to know the electric field there, again, I could calculate it as long as I knew this charge and this distance. And again, I know the direction. It would be away, right? So we can get directions because it's always a direction a positive charge would move. So you have to sit back and look at it and say, okay, if I put a positive charge there, would it get pulled towards it? Would it get pushed away from it? Those are our only two choices. Which brings us to electric field lines. Electric field lines allow us to visualize the electric field, right? There's nothing actually there, but electric field lines tend to be very helpful. Again, it's another way of diagramming situations, and I think we all know diagrams are important for all of the things that we do. So electric field lines allow us to help diagram the situation and explain what's going on. There's some rules for electric field lines. They're always drawn from the high potential to low potential. And what does that mean? Well, we'll work on that. Two electric field lines can never intersect each other, right? If electric field is the force per charge and lines cross each other, that means there's a choice for which direction it's getting pushed. At any one point, there is one net force, right? If two lines are crossing and say, oh, well, there's two forces, well, then we'd add them together and get a net force. So no matter where we're looking, electric field lines can never cross each other because that means that kind of the charge has a choice of which way it wants to push. That's not the case. So this one is just good to know. There's always some professor that wants to, see if you read the fine points. Inside a conductor, inside a wire, or anything that conducts electricity, the electric field is 0. Take that for what it's worth. This is important. We're going to have to explain it more. This is definitely important. We're going to have to explain it more. And they go outwards from a positive charge, inwards from a negative charge. So what does all that mean? Well, let's look at some examples. Here is an object that has a negative charge. These are the electric field lines. If I put a positive charge anywhere around this, it would get pulled towards it. So if I was drawing electric field lines, I would simply be drawing lines that come in. None of these lines will cross each other. Even if I put more of them in, we all kind of got a feel for which way they would go. So they don't cross each other, and they go inwards towards that charge. If I had a positive charge, which way would the field lines go? Well, a positive charge would get pushed away, so these lines still don't cross each other, and they're getting pushed away from this charge. So in both cases, these lines are showing how a positive charge would move. If we look at a couple other ones, if I had two positive charges, well, if I put a positive charge, it would want to move away, but it would want to move away from both of them, right? So if I put it over here, it'd simply move away. If I put it over here, it'd simply move away. But if I put it here, well, this one would push it away, but then this one would start pushing, so it would start to deflect it upwards, or it would start deflecting it downwards. So as we start to look at kind of more complex situations, we can draw these electric field lines and get a feel for not really how the charge would move, how a positive charge would move, but how a positive charge would get pushed. And there is a difference there, right? If I put a positive charge here, that doesn't mean it's necessarily getting pushed or it's going to travel along this line. It's going to get pushed this way, and then it's going to get pushed more to the right. But that doesn't mean it's going to stay on this path. All right, so let's look at a situation where I establish an electric field. So I have this charge, this black positive charge. I could change it from positive to negative if I wanted. We'll leave it positive. That's perfectly fine. And I'm going to bring other charges into this, and the charges I bring in won't move. They are fixed charges, right? So I could already see if I put a positive charge there, it's going to push this one. I could also see as I look around, I could see the electric field lines produced by this positive charge, right? As I move this red one around. So if I put it here, that would push another positive charge away from it. So there we go, bam, and we got scored a goal. It's not the goal, but there we go. Now, if I added more charges, well, all of a sudden each electric field of one has an effect on the other. Here's the three forces that they're exerting, right, which in the end doesn't show me the net force, but still I could see how the electric field would be traveling, or what direction the electric field would be pointing, right? I could add some more, and I could add some more, and so that doesn't mean this charge is now going to follow exactly along the lines. That means that's how it's going to get pushed, right? So there we go. I'm going to do something like that. If I added some more, I have no idea what's going to happen with it, but it's going to do something like that, right? Because each charge is going to push it. I could also add some negatives, which would again show how the field is now going, because it's going to get pulled towards those. If I put the charge back, we could see the electric field lines, which would show how it's going to get pushed. I want to make another goal, so I'm going to maybe pull it down here more, and maybe it's going up, so I'll add a positive charge. It's going to push it down, so it's going to kind of push it this way. Let's see. And, oh, so close, so close. All right, one more try. But we could see these electric field lines. We could see that they would push a charge around according to the electric field lines. All right, so there we go. There's the start of electric fields, which still, electric field, electric force, they're they go hand in hand with each other. So hopefully you see that. You can calculate the electric field, you can calculate the electric force.